Welcome to week 8. We're almost halfway through. Um, so we finished off last week by talking about pi bonds reacting as bases in order to make carbocations. And so we're going to start off this week by talking a little bit more about carbocations and kind of what are the things they can do. Because by now we've seen carbocations do a couple of different things. Um, and so we're going to add to that, add one more thing. And the big one that we're going to talk about is rearrangement. And rearrangement gets to this idea of stability of carbocations. So if you're unsure on the stability of carbocations, definitely go back and make sure that you understand that before we jump into this new idea of rearranging carbocations to make them more stable. Okay. So rearrangement of carbocations. So as you'll recall, if we talk about the stability of carbocations, there were two main factors. Right? Factor one was substitution. If you put your carbocation on a tertiary carbon, that is going to be much more stable than a secondary carbon, which is going to be much, much more stable than a primary carbon, right? Primary carbocations don't really exist, do not happen, right? And so tertiary carbocations are more stable and secondary carbocations are okay, right? The other thing that stabilizes carbocation is resonance. We're going to focus mostly on substitution today because substitution is the one that gets affected most by rearrangement. So let's do an example. I'm going to take a really simple alkene here, and we're going to make a carbocation out of this. So we're going to treat it with a strong acid. I'm just going to use HBr. Right? As we know, alkene plus strong acid gives us a carbocation, and so we use the pi bond as our base. We come add to this hydrogen, make a sigma bond, and break a sigma bond, right, to generate the most stable conjugate base, which is Br minus. And so you've seen this kind of thing happen before, right? The hydrogen goes on the less substituted position, our primary position, right? While the carbocation ends up on our secondary position, right? And so this is Markovnikovs rule, right? Markovnikovs rule says cation goes on the secondary carbon, which is great. That's a nice rule. It's easy to apply, right? We look at these two carbons. We say this carbon is attached only to one other carbon, so it's primary. This carbon is attached to two carbons, a carbon on this side and a carbon on that side, so this is a secondary position. And now we choose where do we put the carbocation. We always put the carbocation on the more substituted position. That's Markovnikovs rule. Right? But what you'll notice is that, of course, there is a tertiary carbon right here. So we can't put the carbocation on the tertiary carbon to begin with because it's not a part of the alkene, right? The pi bond that we're breaking doesn't have any electrons that it's sharing with that tertiary position. So when we use those electrons to make a new sigma bond, the tertiary carbon can't give any electrons away to become a carbocation. But what can happen is that now that we have a carbocation, right, we can see that we have, so this hydrogen, we have all these electrons in these sigma bonds. A tertiary carbocation is going to be more stable than a secondary carbocation, and so we can move this sigma bond over to this position and create a tertiary carbocation. Okay. This is rearrangement. Right? So rearrangement happens basically to create a more stable carbocation. When does rearrangement happen? Two things have to be true, right? We have to move electrons from a neighboring carbon, right? We can't move electrons from all the way across the molecule. It has to be from a neighboring position. And we're always going to move sigma bond electrons, right? So In this case, we move the CH sigma bond from the tertiary position to the second position. So we'll always be moving sigma bond electrons. We're going to move from a neighboring carbon. And secondly, it has to result in a more stable cation. Right? So we have to go from secondary to tertiary, right? Start from a secondary cation and create a tertiary cation, something that's more stable. The product has to be more stable than the starting material. This is the same idea as acids and bases, right? In acids and bases, we always create the more stable products, right? That's the side of the reaction that's going to be favored. Same thing with carbocations. If we can make a more stable carbocation, that's the side of the reaction that's going to be favored. So rearrangements occur when we can move a sigma bond from the neighboring position over and create a tertiary carbocation in the position that gave up those electrons. Okay, so we'll do some examples and you'll see how this, what these kinds of things look like when we use this. So what happens to finish this off, right? Of course, now we have a carbocation, so the bromine can come in and attack that tertiary position, and we'll get a tertiary alkyl bromide out of this reaction, right? The hydrogens are still here. I'm not going to draw them. Well, we can draw them in. These two hydrogens are still here, but we get a tertiary bromide, even though the tertiary position wasn't a part of the double bond there. So these rearrangement products will look kind of weird because all of a sudden you'll have a conjugate base that's attached at a position that wasn't a part of the double bond at the beginning. But the reason that occurs is because it's rearranging. Okay, so more examples in the next video.